Hi guys, this is a topic of halogen and alcohol. So today I'm going to discuss about the questions from this tutorial. So first let's revise a bit on the learning outcomes. The first one is able to recognize and name halogen according to IUPAC system, able to describe the mechanism of nucleophilic substitution, SN1 and SN2, knowing that SN1 is for a tertiary structure, SN2 is for primary and secondary. Now, just for your information, secondary can actually undergo both SN1 and SN2, but preferably SN2 in this case. So for the third one, able to describe and explain hydrolysis, formation of nitriles, formations of primary amines of halogen alkanes. Now these three chemical reactions or organic reactions is under the same mechanisms of nucleophilic substitutions. All right. Next one is able to recognize and name alcohols according to IUPAC system again. Next, you must able to classify and explain what is primary, secondary, and tertiary alcohol because these will explain why its chemical behavior when it reacts with an oxidizing agent, reactions of sodium, dehydrations to alkanes, formations of halogen alkanes, and formations of ester. Right? Let's look at question number 1. Now, haloalkanes are suitable compounds from which to synthesize other compounds. The flow diagram below shows how compounds can be prepared from 2 bromopropanes. So it started with 2 bromopropanes here. Okay, and then it reacts with reagent X to get C3H7CN and reagent Y to give C3H7OH. So, of course, based on these flow diagrams, if we can, before we look at the questions, it is good for us to identify all of them, the one that is possible. So let's start with reagent X. So when I have 2 bromopropanes, so first you need to know the structure of 2 bromopropanes, which is a propane, 3 carbons, and then with a Br group at carbon number 2, 2 bromo, and the rest will be, as usual, hydrogen. All right. Now, in this case, this is a halogenoalkanes, which means we have to identify whether it's primary, secondary, tertiary, so that we know it is actually going through SN1 or SN2. Now, obviously, in this case, I have the alpha carbon here, and this alpha carbon is attached to 2 other carbons. Therefore, this is a secondary structure, which means it is SN2. But nothing wrong if you actually draw the mechanism for SN1, because it can be both anyway. So in this case, what reagent will we use until we can get C3H7CN? Now, if you look at the structure of 2 bromopropanes, as well as the final product here, C3H7CN, right? We can check the difference in terms of its structure, the molecular formula. So I have 3 carbon initially, at the end, still 3 carbons. I have 1, 2, 3, 4, 5, 6, 7, 7 hydrogens beginning, now still 7 hydrogen at the end. So the only difference between the 2 bromopropane and the C3H7CN is the Br and the Cn. So obviously the reagent X here is KCN or NaCN, any metal cyanide, and it should be in ethanolic conditions, dissolved in ethanol, and it should be heat reflux in order we get this. All right, it's a substitution reactions until we get same structure here, just that the Br substituted by Cn. The rest remain the same. All right, and how do we name this? Again, the same thing. We always start from the functional group if there is a carbon or closest to the functional group. In this case, Cn is the functional group. This is carbon number 1, number 2, number 3. We take the longest chain, still 3 carbons, right? And this one, that out of the numbering, we call that as a branch. So this branch has 1 carbon, so it's methyl. So overall, the name is 2-methyl because it's attached to carbon number 2. And then I have 3 carbons, the longest chain, so it's propane, right? And because I have a CN group, so is propane nitriles. So that's the full name for this product. Okay, so that will be for reagent X to get C3H7CN, right? So let me erase that and then we move on to what happened to the reactions, the further reactions after this, which is the hydrogen plus. right? The hydrogen plus. What happens if the product is subject to an acid in aqueous form? So then let's start with that. So we have the original compound just now that I have substituted by CN. All right. And then now it reacts with acid, dilute acid. Okay. So whenever you react with an acid with the presence of a CN group, yes, this will happen. We call that as acidic hydrolysis. So you actually break the CN apart, then you will get CH3, CH, C, CH3, all remain the same except that the CN split apart. And this C with the CN just now, with the nitrogen just now initially, it turns into COOH. It turns into a carboxylic group. So it's a carboxylic acid now. And what happened to the nitrogen? The nitrogen will react further with the excess of hydrogen ions because it's in acidic conditions. You will get NH4 positive ammonium ions. But the more important thing here is to identify the resulting organic product. So this is the structure. And how do we name that? As usual, we start from the carbon here because it's the functional group 1, 2, 3, the longest chain, and this will be the branch attached to carbon number 2. So it's 2-methyl 1, 2, 3. So it's a 3-carbon carboxylic acid. What's the name? So it's propanoic acid. Okay, so that's the product. And this thing you have to double check, right? With the molecular formula given C3H7COOH. Yeah, it matches with it. So yes, this is the correct answer then. All right, so that's when they react with acid. Next, we shall look at what happened when the 2-bromopropane actually react with a reagent to form compound P, which have the formula of C3H7OH. Now, obviously, from the formula, we can make a guess here that in the presence of OH is probably an alcohol. Let's check the structure again, right? So it's C3, 2-bromo, the rest OH, and then it changes into compound P, also C3H7. So everything the same except for the Br. And the Br now it turned into an OH or substituted into an OH, then you get an alcohol. Right? So this is a structure. Of course, the rest will be hydrogen. Okay, and what happened next is we have to identify what reagents should we add in order to substitute the Br. So in this case, what would you suggest? It's actually NaOH aqueous heat reflux. And why is it heat reflux? Again, most of the organic compounds are highly volatile. And in this case, since we are forming alcohol, alcohol is the one it's well known as with high volatility. All right. So therefore, we have to heat reflux. So NaOH will be the reagent with OH as a nucleophile. In this case, again, it is a secondary bromoalkane and it turns into a secondary alcohol through SN1 or SN2 because this is a secondary structure. It can be both. All right. So compound P is actually a secondary alcohol, and this one just now is a 2-methyl propanoic acid, as we have deduced, right? So what happened when compound P reacts with this carboxylic acid? Okay, and then both combine, you will get compound R, right? So now let's check what happened. P is an alcohol, another compound is a carboxylic acid. All right, so it's quite obvious now. It is an esterification reaction. So to form ester, an alcohol with a carboxylic acid forming ester. All right, and how they actually form the ester, let me show you. First, I have a secondary alcohol here. Now I draw the structure in such a way that the OH is pointing towards the right hand side. See that, the functional group? I mean, I'm trying to make the functional group pointing to each other. from both alcohol and the carboxylic acid. Why is it so? Because, yeah, esterifications. So when these two, carboxylic acid and alcohol, this is compound P, that's a carboxylic acid. So when these two react together under a conditions with concentrated sulfuric acid, right, heat reflux at 60 degrees Celsius, this is an esterifications, and for an esterifications, we shall remove the OH and the H to form water. All right, so the OH from the alcohol, and then I will get the resulting structure of CCC, same, without the OH, of course. And here from the carboxylic acid, all remain the same except this, the COO without the H, because the OH and the H will actually give us the byproduct of H2O, and the remaining structure here will be the C connects with the O. So this is how we get an ester, COOC, COOC. So that's an ester, okay? And that is compound R. Okay, so this is how we get the structure of compound R. So as long as you know what's going on during a specific reactions, right? Like in this case, esterifications, you are supposed to remove water, remove one OH and one H group from carboxylic acid and alcohol, and then you will get the resulting structure by combining the remaining structures from both. Okay, so now you get a compound R. That's it for R, and next look at structure Q, right? Compound Q, what is that about? So let's check the conditions. So from an alcohol, which is compound P here, let me redraw it again. P is a secondary alcohol, okay? It's a secondary alcohol, the rest all hydrogen, of course. And now this thing is going through reactions with concentrated sulfuric acid at 140 degrees Celsius. Now, can you see that? If you notice, both are concentrated sulfuric acid. They use the similar reagents. The only difference between them would be the one on the right-hand side, they are reacting with the carboxylic acid. So an alcohol react with the carboxylic acid, as I said, it's always an esterifications reactions. But in this case, an alcohol with a concentrated sulfuric acid without a carboxylic acid. So what would it be? Now, concentrated sulfuric acid is a very good dehydrating agent, which means whenever you use concentrated sulfuric acid, it's always removing water. Just now, when we have alcohol and carboxylic acid, they are actually removing water from it so that you get an ester, right? The byproduct was a water. And in this case, we having an alcohol alone, and we are adding concentrated sulfuric acid. So obviously it's going to remove the water as well. But then this water molecule is going to remove from a single alcohol. And how can we remove that? I show you in the class. So in this case, should be the OH group, and then you remove another H from the adjacent carbons, which means the carbon next to the alpha. Now this is the alpha. You can remove from either one of the carbon, either the one from the left or the one from the right. Either way, up to you. If you remove from the left a hydrogen from here, then this bond will move up to form a double bond, to form an alkenes. So the resulting product will be double bond here, CH, and then the rest remain the same. So byproduct will be water. You still remove water, always remember that, dehydrating agent, and you get an alkenes here. So the name for this is a propene. All right, so compound Q is actually a propene. This is the structure formula. All right, so we have identified everything just based on the flow diagram, in fact, and next we're going to answer the questions from what we have deduced. All right, now let's look at question 8. Draw the structure formula for 2-bromopropenes, which we have done it. Which single term is used to describe reagent X and Y? Right? What is that X and Y? A single term to describe reagent X and Y. Now X, just a reminder, KCN or NaCN, and Y is actually NaOH. Now both consist of OH and CN. They're both having lone pairs. So what is the term used? Nucleophile. Right? Is something the lack of electrons, a molecule or ion or a species, the lack of electrons, not lack of electrons, actually with at least one lone pair of electrons. All right, that's why we call it as nucleophile, not lacking. The one that lack of electron, we call it as electrophile. So this is nucleophile. And then for part C, the equation for the reactions that produces compound Q, wow, it's actually given. Let's check it out. So see that compound Q here, the equation given is actually showing an ether, right? It's actually showing an ether. And what we deduced just now, compound Q, it's actually an alkenes, concentrated sulfuric acid, right? So now how do we know whether it's forming alkenes or ether? Now in this case, it's very simple. You guys may actually ignore this forming ether. No, because we don't actually learn about ether, right? We don't actually don't learn about ether. So we can ignore these equations and assuming that in this case, we just focus on one, which is when you use concentrated sulfuric acid, you're getting an alkenes. Okay, but for your information, if you're using concentrated sulfuric acid at 140 degrees Celsius, you will get alkene, you will get an ether. But if you change the temperature, you actually get an alkene. All right, but like I said, we only focus on one thing, which is dehydrations. We are forming an alkenes then. All right, that's compound Q, so we can ignore this, right? For D, since we ignore that, we don't have to do this. But anyway, it says that draw a structure formula for an isomer Q that belongs to different homologous series. Now, when they say structural formula for an isomer of Q that belongs to different homologous, meaning that this Q is actually an ether, and we can actually change it into something else where it is not an ether but maintain the same formula. I mean, this can be, you can try it out as a bonus. How do we do that? Let's work it out, right? I can show you that, but always remember, you don't need to know anything about ether. Now, let's check it out. We have this molecule as compound Q, let's say. We are going to draw an isomer for it. So 1, 2, 3, 4, 5, 6. So C6. H will be 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 14. And I have one O in between. C6H14O. Okay, so we need to draw another structure or another isomer where it is not an ether but maintain the same molecular formula. So what would you suggest? Can it be an alcohol? Let's check it out. 6 carbon connected to each other. All right, and then maybe it is an alcohol, so I put an OH here, and the rest all attached to H. So I'm not sure whether it matches with this. Let's count. 1, 2, 3, 4, 5, 6, 6 carbon, yes. 14 hydrogen, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, yes. And 1 O, done. So it matches, therefore this is hexanol. So this could be the answer for D, an isomer of Q. All right, and then for part E, draw the structure for R, which we have done it. R is actually an ester, I showed you before, and describe briefly how to distinguish between compound Q and R. That's a very good question. How to distinguish between Q and R. Now, Q is an ether, which we don't learn it. Let's see what we can do with R. Now, R, like I said, is a carboxylic acid, right? So if it is a carboxylic acid, how can we test it so that it is different from ether or different from any other compounds? Not only for ether, in fact, to test or to distinguish carboxylic acid from the rest of the homologous series, you can actually use carbonates. So it's either sodium carbonates or potassium carbonates. Any carbonates. Why? Because carbonates will react with an acid to form carbon dioxide gas. And this thing will not happen with any other homologous series. Alkane, not really. Alkenes can't react with carbonates. Alcohol, no reactions at all. Halogenoalkanes, no reactions as well. So in this case, only acidic organic compound can react with carbonates. In this case, we only have carboxylic acid under organic chem, right? So therefore, to distinguish carboxylic acid from any other homologous series, carbonate is used, and the expected observations right, will be effervescence. And the gas produced is actually a carbon dioxide gas, which we can test it using a lime water, right? Later it will turn milky. All right, that's for F, to distinguish carboxylic acid from anything, not only from ether, from any other homologous series. And for G, name the organic compound produced on oxidizing compound P with acidified potassium dichromate solutions. Now, what is that compound P again? Compound P is actually this, a secondary alcohol, which I'm going to draw it again here so that you know what's going on. Now, this is P, which is the secondary alcohol. The rest all H, right? That's P. And P is oxidized with acidified potassium dichromate. What is that acidified potassium dichromate? It's actually K2CR2O7/H+. That's acidified potassium dichromate. And this is known as an oxidizing agent. Okay, so we know that this is actually a secondary alcohol. And what would you get if you oxidize a secondary alcohol? You're supposed to get a ketone. Okay, and let me show you again how does it work and how does it actually form the ketones. First, to oxidize an alcohol, we need to remove 2 hydrogen, one from the OH, one from the same alpha carbon, which is here. Then this extra bond is coming in to form a double bond. Therefore, you will get a product, which is like that. The rest remain the same because I only remove 2 hydrogen. So in this case, you're getting a ketones. This is a ketones, and ketones can be further oxidized. So that's it. This is a structure. All right. And they want you to name these ketones. How many carbons here? 1, 2, 3, right? So the longest is 3 carbons. So it's propanone, N-O-N-E. Okay. Ketones, propanone. So that is the answer for G. And what's the observation here? If you're using dichromate, it's supposed to change from orange originally and turn into green if it oxidizes anything, because if you oxidize some other compounds itself, the dichromates will actually get reduced and it reduces to chromium 3+. That's why it turned into green color. All right, so that's about it for question 1. Let's move on to question 2. So consider the reaction sequence outlined below. So first we have, okay, it may not be clear here, it's actually C2H5OH. Okay, and what happened? Go through a reagent A to form C2H5O minus. Sorry, the things blur. So it's actually C2H5O minus. From OH turned into O minus by remover of hydrogen. And then the next one is a secondary alcohol going through reagent B. It turns into C3H7Cl. Okay, so they form an ether. Again, anything related to ether, we just ignore it. We don't need to know. So I don't want to confuse you further, right? But then let's see what's happening here. So give the name of ions number 1. So what is the name of this C2H5O, right? C2H5O minus, it's actually named as etoxide. Oops, sorry. Etoxide. Why am I keep my bad? Okay, etoxide. Now, why is it etoxide? Etox, eth is actually ethane, right? It's 2 carbons, and then with 1 oxygens only, like an oxide, sodium oxide, magnesium oxide, O minus now. So therefore, hydroxide, right? So ethane plus oxide, we get etoxide. So that's the name of the ions, right? So A is done. Okay, B, name the region A and B. Now let's check what happened here. Now from here to here, what do you think? You're removing hydrogen from it to form etoxide. So what reagent can be used? Now, very obvious in this case, when you're removing hydrogen, we can do this. It's actually a test for alcohol, C2H5OH, right? If you mix with sodium metal, you're actually changing into sodium, is sodium etoxide plus hydrogen gas. All right, this is actually a redox reactions. Now, why is it a redox? If you check the oxidation numbers from sodium here, which is 0 solid, into sodium plus, this is an oxidation reactions. And of course, if this is oxidation, that will be reduction, right? So if this is reductions, we check the oxidation numbers. Initially, OH is covalently bonded, and now they change into O minus. Yeah, obviously you're getting electron, therefore it turns the whole thing into negatively charged. So it's a redox reactions. All right, and the observation here is formations of hydrogen gas, and that's why by adding sodium metal into an alcohol is a test for alcohol. Because if I give you an unknown liquid which is colorless, which you can't actually see anything, no precipitate, no color change, but then if you drop a small little lump of sodium metal into it, you can see a vigorous effervescence reactions. And this effervescence, you will test it with a lighter splinter, and the lighter splinter will give you a pop sound. And that means hydrogen gas release. All right. So if you see a hydrogen gas release by putting a sodium metal into a test tube or a solution, that solution most probably is an alcohol because of the OH group, right? Generally, any organic compound with OH group can react with sodium metal to give hydrogen gas. All right. So other than alcohol, what you can think of, okay, what you can think of that actually consists of an OH group, carboxylic acid. Okay, because it's COOH, you have an OH group. So anything with an OH group can react with the sodium metal to form hydrogen gas. So this is actually a test for it. Okay, so then that's what happened. So reagent A here we can identify as sodium metal. All right, and what about reagent B? Let's check it out. Let me erase the rest. So if you look at reagent B, it is actually changing from a secondary alcohol into C3H7Cl. Again, it is not clear. Apologize for that. So what do you think? You're changing it into C3H7Cl. Obviously, this is a halogenoalkanes, and here they give you a hint of a secondary alcohol. So from an alcohol, let's say this alcohol is having an OH group, and then it changes into something with Cl. Obviously, this is nucleophilic substitutions. And how to turn an OH group into a halogen. Still remember, I list down the possible reagents that we can use to change an alcohol into RCl, right? Substitute the OH with Cl. So what are the reagents here? Now the reagent can be PCl3, PCl5, SOCl2, or even HCl. PCl3, heat reflux. This one, room temperature. This is heat reflux. Same goes to HCl, also heat reflux. All right, this is a special case, but you can choose either one from here. It will turn your OH into Cl. Okay, and draw the full structure formula for compound 2, which is the ether. We don't need to know this, so we can ignore this for the moment. And let's look at question 3. Okay, now question 3 is, good thing is they give you the equations, you just need to draw the structure out and then you name it. Now, halogenoalkanes or haloalkanes can undergo substitution reactions with ammonia. This is nucleophilic substitutions. Draw and name the organic products of the following reactions. Now, here, with a Br with an ammonia, you have to look at this. A halogenoalkane is actually delta negative, delta positive, and the ammonia is actually with lone pair. This is a nucleophile then. Okay, so this is the nucleophile, and therefore what we're going to do is this NH3 is going to attack the C and the CBr bond break, going through either SN1 or SN2. In this case, which one? Right? So this is a primary structure, and of course, it will go through only SN2. All right, so you will substitute it. Still remember, you have to remove one hydrogen. Nitrogen can only form 4 bonds. If you attack the C, you will get to remove one hydrogen. So in this case, the final product should looks like this. NH2, right? That's the final main product. And at the end, you will have a byproduct of HBr. But that's not important because they want to draw and name the organic product. This is the organic product. This is not the organic product, unless they ask for a balance equations. And what's the name of this? Now the name is very simple. Whenever you have NH2, it calls amines, and then now how many carbons here? 2 carbons, right? This 2 carbon will name as a branch, so ethylamine. That's the full name. If you have 3 carbon, then it's propylamine. 4 carbon butylamine, right? As simple as that. And next one, the same thing. Um, oh, I'm sorry, guys. I miss out the alcoholic conditions. Haha, my bad. So, if it is aqueous, that's what happened, like what I explained. But then, if the ammonia is actually under alcoholic conditions, um, in fact, not much of a difference. It's just that you won't get water, but that won't affect the final product. No, yeah, that doesn't matter. No problem. All right, it doesn't matter. It's okay. And in this case, the next one is the same thing. You draw the 4 carbons, right? And then you have a Cl here, but this Cl is going to replace by the NH3, so therefore you will get NH2. All right, you will get NH2, so you will get an amines as well, but this one is 4 carbon, so butyl as a branch, 4 carbon, amines. And the byproduct, yes, is HCl, which is not important. Alcoholic will have, yeah, let's just ignore that. The main organic products, this is what they want. Okay, and next one, haloalkanes can undergo eliminations reactions. Okay, it's stated clearly here, elimination, so we know what to do. Complete the following reactions by drawing and naming the organic product. Again, if I'm using KOH under alcoholic conditions and its eliminations, we are not actually using the OH to attack the carbon. No, we don't do that. Although it's delta positive and delta negative here, we are not doing nucleophilic substitutions, but rather we are doing elimination. So the OH here is going to attack a carbon from the adjacent, attack the hydrogen from the adjacent carbon, remove this, the bond move up, and then break the CCl. You see that clearly? Let me show you again the arrow. So it should be from this, attack the hydrogen next to the alpha. So these bond break, come up to form a double bond, and this carbon, the alpha carbon, will have 5 bonds for now, and you have to give up one of them. This is the third arrow. So this is a shortcut for elimination 1, 2, and 3. So you will get an alkenes, CH3, CH double bond, CH2, plus HIT, plus KCl, in fact. Right? So this is how you get the product. And what's the name of this product? Propene. Simple. Okay. And the next one is again NaOH in alcoholic conditions under eliminations, so that it will attack the hydrogen next to the alpha, which is this. This is alpha carbon. So bond move up, break this. So 1, 2, 3, and you will get a simple ethene here, plus NABR, which is not important. Again, as I said, so organic products, this is what they want. So just show this and this. Of course, this is ethene. All right, very simple. Okay, 4. Part A, explain why haloalkanes can react with nucleophile. Why nucleophile attack haloalkanes? Okay, why haloalkane is susceptible to nucleophilic attack. So what structural features in these haloalkanes attract the attention, draw the attentions of nucleophile? Because haloalkane has a delta positive carbon. That's the main reason, because this alpha carbon or delta positive carbon, it's always attached to a delta negative halogen, right? Because of this delta positive carbon is lacking of electrons, nucleophile will love it, because nucleophile has at least 1 lone pair. So they love to attack anything that is positive or delta positive. So due to the presence of a delta positive or partially positive carbon, okay? Or partially positive alpha carbon, that would do. That's A. And part B, write equations and give the mechanism for the following reactions. Now we have 3 options here. I'm going to show you only 1 out of the 3. I'm going to show you this. In class, I've shown all of them, right? I'm just show you the second one. If you need help with the rest, let me know, right? I'll show you in the class. So in this case, we have 2 chromopropane. So 1, 2, 3, 2 chloropropane. This is a structure. The rest are all hydrogen, right? And this thing is going to react with potassium cyanide, which is KCN. Okay, KCN. Okay, now don't misunderstand this. KCN is actually an ionic compound where K metal ion do nothing, so might as well I just show you Cn minus here. Okay, so the lone pair from the Cn is actually going to attack the delta positive carbon, delta negative, is going to attack the delta positive carbon, all right, because this is secondary. I'm going to show you SN2. Then what happened? You will get a transition state where you have alpha carbon here, dotted line with original Cl, dotted line with the Cn that newly attack it, and the rest will be hydrogen here, and the other two will be CH3, CH3. I'm drawing this to CH3. You must be able to see it in that way, right? So then you have to show the bond breaking between CCl because they choose to have Cn rather than Cl. And now you get your final product. Then you can draw the usual way, CH3, CH, CH3. You can draw back exactly what it shows you at first. And then you have your Cn here instead of Cl. So this is SN2 reactions. Okay, this is under SN2 because 2 species involve 1 and 2, therefore is SN2. Now, since this is a secondary structures, right, I can show you in different mechanism, which is SN1, right? So what will happen in an SN1 mechanism? So same product, the same compound, a secondary propane. Because it's a secondary, like I said, it can undergo 2 different mechanisms. So now, delta positive, delta negative. So the bond break by itself, okay, because it's secondary, it forms a rather stable carbocations. So in this case, you will get a carbocations in between. The rest all hydrogen, guys. Okay, now then the Cn minus with the lone pair involved attack the carbocations to form the final structure, which is the same as just now. You just need to split it into 2 steps then. Okay, so now you see that you have a CCN. So this one is step number 1. This is step number 2. Since the first step, the very first step involved only 1 molecule, hence this is SN1. See that? SN1, you will get a carbocation as an intermediate. SN2, no. You will get a transition state and straight move on to the products. So this is how it looks like. Okay. Okay, number 5. Suggest giving reasons which chloroethane, bromoethane, or iodoethane will react fastest with sodium hydroxide. Okay, which one react the fastest with sodium hydroxide? And first, you need to know what reaction it is. So when chloroethane, let's say CH3, CH2Cl reacts with sodium hydroxide, okay, it did not specify the conditions because NaOH can be in aqueous or alcoholic. If it is aqueous, then it's nucleophilic substitution. If it is alcoholic with OH, that will be elimination. Now, since this case, it doesn't specify, so we follow the by default. Remember that by default will be aqueous because NaOH is a base that highly soluble or fully soluble in water. Remember that. So in this case, what reaction they're talking about here is actually nucleophilic substitution to get CH3, CH2, OH plus NaCl. And they want us to tell why chloroethane, which one react the fastest, the rate of them. So in this case, we have to check. Now, since they are all the same, Br and I. So bromoethane, iodoethane, all plus with the same reagent NaOH, and you get the respective alcohol. All form the same alcohol. It's just that you're forming different byproduct, of course, NaBr and NaI. But which one is the fastest? Now, in this case, we can see Yes, it's a nucleophilic substitution. The OH is substituting the Cl, Br, and I. The main thing here is you must able to break the bonds, right? You must able to break the CCl bond, the CBr bond, and the Ci bonds. Now, in this case, CCl, CBr, and Ci, which one is the strongest? Now, based on its atomic structure, the atomic radius, Cl is the smallest. So what I can say here is CCl is the closest to each other compared to CBr because Br is bigger, the outer shell is much further away. So the distance between C and Br will be further. And of course, Ci will be even further. So in this case, CCl is the closest, therefore the attractions or the share pair of electrons between the nucleus will be the strongest. All right, so the bond energy for CCl is the strongest, followed by CBr and Ci. So if that's the case, CCl is the strongest, it will take longer time. It will definitely need longer time for that because you need to absorb energy and break the bonds, right? And which one is the fastest? So the fastest will be the one with the weakest bond. So Ci or iodoethane is the fastest. This is in between the medium speed, and this is the slowest. You see that? So you explain in terms of bond energy. CCl bond is the strongest, therefore it's the slowest. Ci is the fastest because it has the weakest bond energy. That's about it for number 5. Okay, last questions. I guess this is the last question, number 6. 1-bromobutane will undergo reactions when heated as shown by reaction A and B. Now I have bromobutane go through reaction A, I'm getting an alcohol. What is that reactions? Obviously, if you check the formula for both compounds, the only difference is the Br and the OH, and it is a substitution. So what reagent do we use for A? NaOH, right? And it should be in aqueous. It's a nucleophilic substitution. And for this B, they're actually changing in halogenoalkanes into alkenes. And if you check the formula of these two molecules or these two compounds, you can see that the difference between them is actually HBr. You are taking out HBr from it to form an alkenes with the double bond. So this is an eliminations reactions. And what reagent to use? Same. In fact, it's NaOH. But the condition is not aqueous, but in alcohol or ethanol, alcoholic NaOH, right? So that's the main difference here. Like I explained just now, you use the same reagent, but you put into aqueous, you will go for nucleophilic substitution. If you put into alcohol or ethanol, they will go for eliminations. So that's A and B. Both NaOH, one in aqueous, one in alcoholic. All right, done for A. And let's look at B. Reaction A was repeated using 1-iodobutane instead of 1-bromo. Again, guys, instead of bromine, you are changing in using iodine. So which means this Br is going to change into iodine and go through the same reactions. I mean, reaction A, of course. So, like I explained from the previous questions, will it be faster or slower? Explain any difference in rate of the reaction observed. So what's the answer? It should be the higher rate. It should be faster. Why? Because Ci bond is weaker than CBr bond. So the breaking of Ci is faster, is easier, therefore the time taken for the reaction will be shorter. So therefore the rate of reaction is faster. That's for reaction B. Okay, for C, what type of organic reaction is A? Nucleophilic substitution. And it's primary, right? You can straight away put SN2. You don't have to write the long terms, nucleophilic substitution bracket SN2. You can straight write SN2. That's okay. And for D, show the mechanism for reaction A. I've showed you n times, right? So I don't have to show you again. So this is SN2. You should know what to do, right? Let's move on. For part E, now reaction A was repeated with 2-bromo 2-methylpropene instead of 1-bromobutane. Name the organic compound form, the mechanism for the reactions between them. Now, first we need to draw out the structure because by just looking at the name, if you can see it, that will be good. If you can't see it, I guess you have to draw it out. For me, I can see it. This is actually a tertiary structure. Let's show it up. 2-bromine, 2-methylpropane. So it's a propane, 3 carbons. 2-methyl means you have a CH3 here. Basically, all of them are CH3 for now. And then 2-bromine, so it's the same carbon number 2 because 1, 2, 3. So 2-bromine, 2-methylpropane. Yes, it is a tertiary structure. And this tertiary structure is going to react with what? Reaction A, right? The reagent that we suggest, NaOH. So what happened when you react with NaOH? Aqueous substitution. Take out the Br, put in the OH, therefore you get an alcohol. A tertiary alcohol, that's the product. Because the first one, they want you to name the organic compound form. So in this case, how do we name it? Same, 1, 2, 3, methyl group. So it's 2-methyl, 3 carbons alcohol, propane, 2-ol. Why is it 2-ol? Because the OH is attached to carbon number 2. So propane 2-ol. So that's the name. That's the answer for E1. Okay, that's the simple equations. Next, I'm going to show you the mechanism again, since it's the tertiary, right? So tertiary structure, what's the mechanism? It undergoes SN1, right? So let's check it out. CH3. Let's show you once more. All right, so it should be Br here, delta positive, delta negative. You have to write that, guys, because this will give you marks, the dipole. Otherwise, you can't explain why the bond break and why they are attacking, why you get a carbocation. You can't tell, right? So in this case, CBr, you get a delta positive, delta negative because Br is highly electronegative, and the bonds actually breaks by itself because you are getting a stable tertiary carbocation. Make sense, right? And then now only the OH, because we are adding NaOH, right? OH is the nucleophile with lone pairs. So now the OH minus attack lone pair as well, guys. You may not show all the complete set of lone pairs. You may just show one of them and how they actually attack the carbocations with the curly arrow. And now you get COH with the rest remain the same, which is the tertiary alcohol that I show you. That's how you get a product. Okay, and then of course the byproduct is NaBr, which is not important in the mechanism. This is SN1. So this is the answer for C part 2, right? The curly arrow again, guys, 1, 2, and the product 3, and all the what we call that, the dipoles and the lone pairs all given marks. Okay, so this is the answer for E part 2. Let you erase that. Moving on to F. Now, what type of reaction is B? Go back. Reaction is B, we have identified just now. It's actually NaOH in alcohol to get an alkene, so is under elimination. Right? And if reaction B was repeated using 2-bromobutane, name the other organic products that can form, as well as the product shown above. So if it is not this, let me erase that so it's clearer. If it is not bromobutane or 1-bromobutane, instead they use 2-bromobutane, what would be the product's form in this case? All right, under reaction B. Let's do it again. 2-bromobutane is 4 carbons, and carbon number 2 you have a bromo, so the rest will be all hydrogen, right? And when these things react with NaOH in alcohol for eliminations, what will happen, guys? The mechanism will be this. NaOH, which one they attack? Because now they are in alcohol, you know you are going to eliminate them. This lone pair can attack the hydrogen here or here, like the adjacent, the neighboring, the one next to them, next to the Br. So they can attack hydrogen on this side, which is hydrogen A, let's say, or they can attack hydrogen here, which is hydrogen B. You see that? I'm going to show you this. So if you attack hydrogen A, you will get one product. If you get hydrogen B, you will get another alkenes. So let's draw it out, then you can see the difference. So if I'm removing the hydrogen from A and the Br as well, of course, the double bond will be here in between. So it is actually 4 carbon, the double bond in between them, and the rest remain the same. See that? So this is built to in. But if I remove the hydrogen here instead, the hydrogen B, the double bond will be here. So you must know how the bond move. So then you will get C, double bond C, C, see, the double bond now is at the carbon number 1 and 2 instead of at the middle. So now this is the structure. So this is actually built 1-ene or just butene. In fact, you can just write it as butene. The 1 you can ignore it. So yeah, I don't want to confuse you. So I just put butene then. See that? I get two different products here. This is what they meant. Why two different products? Because butene and butene, they are actually isomer to each other. They are isomers. Why? Because they both share the same molecular formula, same number of carbon, same number of hydrogen, right? The only difference between them is the position of the double bond, which makes them isomers to each other. All right, so that's the products they want. Because butene, you have formed it from this is the butene, and now they ask the other organic, which is this one, butene. All right, guys, and that's all about it. These are all the questions that we need. I'll see you again in class. So I will upload this video as soon as possible, and I will let you guys know. Right? Thank you so much.